Hi guys, this is organic chemistry and we are looking at stereoisomers. So there are different types of stereoisomers. The first one that we are going to look at is cis trans or geometric isomers. So the requirement of a cis trans or a geometric isomer is that there should be a double bond present between two carbon atoms and both the carbon atoms should have the same group present on it. Meaning, if I place an A here, and the same group A should be present on the carbon atom with a double bond on it, but it should be on both the carbon atoms. So the other group, let's call it B. So we will talk about the isomerism with respect to A. So if we have A on the same plane or the same side of the double bond, but on two different carbon atoms with a double bond between them, this is what is known as a cis isomer. The cis isomer can also be if both the A's, instead of being at the top, can be on the opposite side or the bottom side. So this will also be called a cis isomer. The other isomer for this compound will be called the trans isomer, in which we can have the A and the B switching positions on one of the carbon atoms. Meaning, if A stays here, then on the opposite side of the double bond, A would be present below the double bond. So they will be present on the opposite side. Same thing will happen with B. So with respect to A, because we are talking about with respect to A, this can also be with respect to B because they are also the same groups. So with respect to A, since A is on the opposite side of the double bond, this is a trans isomer, and we can also have a trans isomer when the A switches position on the other carbon atoms, meaning on the first carbon atom on the left, the A moves to the bottom, and on the second one, it stays on top, and B also switches position. So here also we can see that group A is on opposite sides of the double bond. So this is what is referred to as a trans isomer. So these are the conditions needed for cis-trans isomerism. Now, the reason cis and trans isomers are formed is because the two groups which are similar being on the same side, if they are very large, they can actually collide with each other and the molecule becomes unstable. So this is what is referred to as steric hindrance. And steric hindrance is completely avoided in a trans isomer because the two groups with the larger sizes are on opposite sides and they will not collide with each other. So that makes a trans isomer more stable than a cis isomer. Another thing that needs to be known is that if we've got two groups of the same type or the same groups on both the carbon atoms with a double bond, but the other two groups are different. So this will also result in the formation of a cis and a trans isomer. So at least one of the two groups present on the two carbon atoms with a double bond should be the exact same. So here we've got a cis and a trans isomer. However, if we have if we have a molecule in which we've got two of the same groups on the same carbon atom, as in the carbon on the left has both the groups attached to it as A, and the other one has a B or a C, or both B's or both C's. This does not satisfy the requirement of cis-trans isomerism because both the same groups are supposed to be on two carbon atoms with a double bond between them and not on the same carbon atom. So such molecules will not show cis-trans isomerism. This is also the case with molecules in which we've got two groups which are same on two carbon atoms with a double bond between them, but the similar group or the same group is present on another side of the same carbon atom present in a double bond. So here we can see that we have two of the same groups on the same carbon atom, while this compound can show cis and trans isomerism together. That is not how cis-trans isomerism functions. We cannot have the same group on the same carbon atom. So such compounds will not show cis-trans isomerism. So looking at an actual example of isomers having cis-trans isomerism present, so we will have two carbon atoms with a double bond, a CH3 group at the top, a Cl group at the bottom. This is a cis isomer, and on either of the carbon atoms, if the CH3 and the Cl groups swap places, this will result in the formation of a trans isomer. So this is an actual example of a compound having cis-trans isomerism. Another example of this compound would be one of the groups being the same, which let's consider the CH3 group as being the same, and the other groups should be different. So in this case also, with respect to the CH3 group, the compound made right now is a cis isomer, and its trans isomer would have one of the two carbon atoms having its R groups switch places. So here the Cl goes up, CH3 comes down. Here the CH3 stays and the OH stays. Since the CH3 groups are on opposite side, this will be referred to as a trans isomer. Now let us consider molecules in which we've got more than one double bond present capable of showing cis-trans isomerism. So a molecule of CH3 CH double bonded to CH, single bonded to a CH, double bonded to a CH, and then single bonded to a CH3 group. So here we can see that there are two double bonds, and each double bond has one of the two groups attached to it being the same. So on the left, we've got two hydrogen atoms, and on the double bond on the right, we've also got two hydrogen atoms. So since there are two double bonds capable of showing cis-trans isomerism, the number of cis-trans or geometric isomers is given by 2 to the power of 2, which is equal to 4 isomers. So power of 2 is the number of double bonds present. So we can generalize this formula by writing it in the form 2 power n, where n is the number of double bonds capable of showing cis-trans isomerism. Now, in order to make these isomers, let's consider their skeletal formulae. So we have two double bonds capable of showing cis-trans isomerism. So we can have an isomer in which we've got both the double bonds showing the cis conformation. So here you can see that we have this same molecule in a cis conformation. How do we know it's in a cis conformation? Because we can see that this and this side has the arrows going down, or the bonds going down, and the other one have the bonds going up. So the opposite sides will have the hydrogen atoms. So hydrogen atoms on the same side of both the double bond means that this is a cis isomer with respect to the first double bond, and a cis isomer with respect to the second double bond. So this is one of the four possible isomers. The second possible isomer would be a cis isomer and a trans isomer. And how do we figure that out? On one of the double bonds, we've got the arrows going on the same side, and on the other double bond, we've got the arrows or the bonds in the opposite direction. So this means that we have the first double bond showing a cis conformation and the second double bond showing a trans conformation for the molecule. Another way in which the isomers can be arranged is if we've got the first double bond showing a trans conformation while the second double bond shows a cis conformation. This can be seen with the bonds pointing in opposite directions on the first double bond and on the same side of the second double bond. So this conformation is known as trans cis. And the fourth possible isomer having two double bonds showing cis-trans isomerism is if both the double bonds show a trans conformation. So here we can see that the first one has one of the bonds pointing up and the other pointing down. And the second isomer also has one of the bonds pointing up and the other bond pointing down. So here the conformation will be called trans and trans. So in this way, we have two double bonds showing cis-trans isomerism, and the combination of the two double bonds showing cis-trans isomerism is cis-cis, cis-trans, trans-cis, and trans-trans. N is the number of double bonds capable of showing cis-trans isomerism, which is 2. So 2 power n is 4. All the 4 cis-trans isomers of this compound have been shown in their skeletal formulae with the conformation present in them. The next type of stereoisomerism is called EZ isomerism, in which the requirement is we have two carbon atoms with a double bond between them, but all the four groups attached to both the carbon atoms must be different. So here we can take the example of A, B, C, and D. In order to better understand this, instead of taking alphabetical examples, let's take the examples of actual groups attached to the carbon atom. So we can have H attached on one side, we can have the OH attached on the other side of the same carbon, a Cl attached to one side of the other carbon atom, and a CH3 group attached to the fourth position available on the carbon-carbon double bond. So now here we've got four different groups attached to the carbon atom. Now the isomerism here depends on the MR of the attached groups. So the next thing we'll do is calculate the MR of each of the groups attached. So we will have an MR or other AR for hydrogen of 1. The MR of OH would be 16 plus 1, 17. The AR for chlorine as 35.5 and the MR for the methyl group as 12 plus 3 is 15. So now in EZ isomerism, if on one of the carbon atoms the higher MR is on one side and on the other carbon atom with a double bond the higher MR is on the opposite side. So in the given example, we have the higher MR of 17 on the bottom side and the higher MR of 35.5 on the above side. So the higher MRs are on opposite. We can also consider lower MRs, but let's just consider one of the two things, either the higher MRs or the lower MR. So the higher masses are on opposite side. Such isomers are called E isomers. E is a German word which is called Entgegen, which is German for opposite. So you can see that the higher M are on opposite sides. So this is the E isomer. And if we switch the two groups on either of the two carbon atoms with a double bond between them, let's switch the one on the left. So if the OH group goes up and the hydrogen atom comes down, whereas on the right, Cl stays above and CH3 stays below. So now we have the higher masses of 17 above and the lower mass of 1 below on the first carbon atom, the higher mass of 35.5 above and the lower mass of 15 below. So here we can see that the higher masses are on the same side, or we can see that the lower masses are on the same side. So such isomers are called Z isomers. Z is a German word which stands for Zusammen, and Zusammen in German means together. So, EZ isomerism is based on the German words entgegen and Zusammen, meaning opposite and together. So, if the higher or the lower MRs are on opposite side, then the isomerism is E isomerism. And if the higher or the lower masses are on the same side, then the isomerism is the Z isomer, or they are together. So opposite side, higher MRs or lower MRs, E isomers, same side, higher MRs or lower MRs is Z isomers. Another type of stereoisomers are optical isomers. Now, optical isomers are also called enantiomers, and they are defined as non superimposable mirror images of each other. So the requirement is the presence of a chiral carbon atom. What is a chiral carbon? A carbon atom forming four single bonds with four different groups or atoms. So here you can see that let's take an example of an actual molecule. So if we have a carbon atom with a hydrogen placed on one end, an OH group placed on the opposite end of the hydrogen atom, a third bond with the CH3 group, and a fourth bond with the COOH group. So here we can see that this is a chiral carbon atom attached to four different groups. So either we will be asked to mark it with an asterisk or to circle the chiral carbon atom. So now this carbon atom has an optical isomer which is a non-superimposable mirror image of this compound. So this is a mirror that is drawn. So the other isomer would be the carbon atom with the H and the OH groups placed in the exact same positions that they were in the first isomer, whereas the positions of the CH3 and the COOH groups have switched. Now, this is the other optical isomer of this compound. So, optical isomers are detectable by the enzymes in the body, and if any compound has an optical isomer present in it, if it is naturally occurring, then it would exist as only a single optical isomer, meaning whether it is the one on the left or the one on the right, if it is naturally occurring, only one of these species would be present. However, if we try to synthesize this compound in the lab, we do not take the optical isomerism into account during normal synthesis. So we will synthesize both the isomers. For example, if we consider amino acid, now one of these isomers is called the L isomer and the other is called the D isomer. Now, which is which need not be known, but we need to know that the names of the two isomers are L isomer and D isomer. So, amino acids, naturally occurring amino acids exist as L isomers, and naturally occurring sugars exist as D isomers, which means that our body is capable of utilizing L amino acids and D sugars. But if we synthesize the amino acids and the sugars in the lab, we end up with a mixture of L and D amino acids, and we end up with a mixture of L and D sugars. Our body is stereospecific, meaning it is capable of detecting the isomers. So L amino acids are the ones that will be beneficial for us, but the D isomers will cause harmful side effects in our body. Same thing with sugars. The D sugars will be beneficial for us, whereas the L sugars will be toxic for us or will cause harmful side effects in the body. So that is why optical isomerism is important, because our body is stereospecific. So what we need to do when we make optical isomers is to identify the number of chiral centers present. And if we need to find out how many optical isomers there are, we use the same formula as used in cis-trans isomerism, 2 power n, where n would be the number of chiral carbon atoms present in a molecule. So taking an example of an actual molecule, we have CH3, we have CHOH, we've got C with a Cl and an OH, and then again we have a CH3 group. So in this molecule, we can identify two chiral centers because this carbon atom has a hydrogen, an OH, a CH3, and on the right it has got a carbon with a chlorine, a hydroxide, and a CH3 group attached to it. So this is a chiral carbon atom. And with respect to the carbon atom with chlorine on it, this is also chiral carbon because it has got a chlorine, an OH, and a CH3 on three sides, and a CHOH CH3 on its fourth side. So this will result in the formation of 2 power n. So here it would be 2 raised to the power of 2, which is equal to 4 optical isomers. And if we are to draw these 4 optical isomers, so let's make them with respect to the carbon on the left. It would be carbon with a hydrogen on the top, the OH group on the bottom with the CH3 group on the left, and the CCl, OH, and CH3 group on the right. And its mirror image would be the carbon with the hydrogen on the top, the OH on the bottom, the CCl, OH, CH3 on the left, and the CH3 group on the right. So these will be the possible optical isomers for the chiral carbon on the left, and for the chiral carbons on the right, we'll need to make some space here. We will have two more isomers present, totaling to four possible optical isomers of the given compound. So the second carbon atom will have a chlorine at the top, a hydroxide group at the bottom, a CH3 group on the right, and a CHOH CH3 group on the left in one of the isomers. And the position of the CH3 group and the CHOH CH3 will switch in the other optical isomer. So let's draw these isomers. So the first one would have a Cl on the top, the OH group on the bottom, the CH3 group on the right, and the CHOH CH3 group on the left. And its enantiomer or optical isomer will have the CH3 group on the left, the CHOH CH3 group on the right, the Cl at the top, and the OH group on the bottom represented in its 3D structure. So these are the four possible optical isomers of the given compound. Okay, now we need to know how to differentiate between the optical isomers. So we use a light source which will have light present in all directions. This is the light that we can see. And then this is inside a device. So this is the light source. And when this light is passed through a polarizer here is a prism called a Nicol prism. This allows light of only a single wavelength or a light in one direction to pass through. This light is known as plane polarized light. This is the light that we cannot see. And when this light passes through the sample containing our optical isomers, there are three possible situations that can occur. Either the light can pass through straight, which means that the mixture that we have is a racemic mixture. We need to know that the mixture we are placing for testing for optical isomers must contain an optical isomer. So if the light passes through straight, it's a racemic mixture, which means it contains 50% L isomer and 50% of the D isomer mixed in equal quantities. If this mixture has the plane polarized light bending in the anti-clockwise direction, that means the isomer present in our mixture is the L isomer. And the L isomer, the full form of L here is known as LEVO, LAEVO, rotatory. That is all we need to know as far as the name of the isomer is concerned. It's called a levorotatory isomer. And if the light is bent in the clockwise direction, that means our mixture contains the D isomer, and the full form of D here is known as dextrorotatory. So how to detect optical isomers? If the L isomer is present, the plane polarized light will bend in the anti-clockwise direction, and if the D isomer is present, then the light would bend in the clockwise direction. And if both isomers are present in equal quantities, which is known as a racemic mixture, then the light will pass through unbent or undeviated. So what we need to know about optical isomers. Naturally occurring optical isomers do not exist in both optical isomeric form, they exist in a single optical isomeric form. And that optical isomer is the one responsible for causing beneficial effects if applied to medicine, because medicine are also obtained from natural sources. If it is a naturally occurring compound containing a chiral carbon atom, that means it will have optical activity, meaning it will bend plane polarized light. So if the naturally occurring compound is present, then it will only cause the beneficial effect. However, if we synthesize this compound in a lab, then we will synthesize both optical isomers in equal quantities, half of which will contain the isomer that causes the beneficial effect, and the other half would be an isomer that is not naturally occurring, and that is the isomer that will be responsible for bringing about the harmful side effects, as is the case in medication. Because medicines do have harmful side effects, which means medicines are not synthesized by separating the isomers. In fact, both the isomers are present in equal quantities. However, there is a procedure by which only a useful isomer can be synthesized, and that procedure is called asymmetric synthesis. It is an expensive process, so it is used to synthesize medication, which is life saving. So, asymmetric synthesis exists, which only manufactures the useful isomer and avoids the manufacture of the harmful or the synthetic isomer. So, in this way, if we synthesize a medicine asymmetrically, then we will avoid the harmful side effects that are present. We can also reduce the amount of the substance consumed, because when we consume a tablet of 1 gram, for example, only half of that tablet is the useful isomer and the other half is wasted. So there is saving of resources. In the long term, there is also a net saving of finances, because lesser amount of medication will bring about the useful effect and avoid the harmful side effects. So asymmetric synthesis is the process by which only the useful optical isomer can be synthesized. And the procedure shown here is the procedure to detect the optical isomers in the lab. However, our enzymes are capable of detecting the optical isomers. So only the useful isomers are bringing about the useful effect in the body, and the other isomer brings about the harmful side effects. Next, what we need to do is we need to identify chiral centers in skeletal formulae of a compound. So, in order to do that, let's take the example of a compound in which we've got 5 carbon atoms present. Here, every carbon atom is bonded to 2 hydrogen atoms, and all 5 carbon atoms are bonded to 2 hydrogen atoms. So, this compound will have no optical isomers present. If we have a compound with an OH group present attached to one of the carbon atoms, so in order to see whether there are 4 different groups attached to it, so we've got an OH on one side, we will have a hydrogen atom attached on the other side, and on the left and the right we have a CH2 and a CH2. But in optical isomers we do not stick to the adjacent positions, we move on in a cyclic compound. So the next positions are also CH2 and CH2, which means that both the left and the right positions are bonded to the same groups. So this compound will also not have any optical isomers present. However, if we have a similar compound, right, in which we've got 5 carbon atoms, but we also have an OH group attached to one carbon and a Cl attached to the other carbon atom. Here we can see that this is an optically active carbon or a chiral carbon, and this is also an optically active carbon or a chiral carbon. How? This has a hydrogen on one side and an OH on the other. The other has a chlorine on one side and a hydrogen on the other. On the left, this has got a CH2 group followed by a CH2 group. On the right of the one with the chlorine, there is a CH2 group followed by a CH2 group. But we can see that on the right of the carbon with the OH, we have a CHCl present, and on the left of the carbon with the chlorine, we have got a CHOH present, which makes it 4 different groups attached to the same carbon atom. So this particular compound will result in the formation of 2 raised to the power of 2, because there are 2 chiral centers present. So 4 optical isomers. If we take another compound in which we place the OH group on 2 sides of a hexagon. So here we can have a hydrogen atom present attached to the carbon atom with the OH, with 2 CH2 groups on both sides, which means that on the left and the right there are the same groups present. There are only 3 types of groups present on the carbon atoms that we were checking. That means this compound will have no optical isomers. Next, let's look at a compound which is also a hexagon, but now it has an OH group on one side of the hexagon and a Cl group on the other side. Now, in this case also, there is a hydrogen attached to both of these carbon atoms. These are two different groups. However, on the left and the right side of both of these carbon atoms, we've got CH2 groups. So there are only three different types of groups attached to the carbon atom having the OH and the carbon atom having the Cl groups attached to it. So this compound will also have no optical isomers. Looking at another compound, we have OH present on one position of the hexagon and a Cl position on another end. So now here, if we look at with respect to OH, we've got a hydrogen attached on the second side, a CH2 followed by a CH2 followed by a CH2 on the left, and on the right we've got a CH2 followed by a CHCl. So that makes the groups on the left and the right different, making the carbon with the OH group attached to it optically active or a chiral carbon atom. So we have one chiral carbon atom with respect to the OH group. Now let's look at the carbon with respect to chlorine. It has got chlorine on one side, hydrogen on the other, a CH2, CH2, CH2 on its bottom side, and on its top side it has a CH2 followed by a CHOH, which makes both the sides having two different groups on it. So this is also a chiral center, the one having the chlorine. So in total here we've got two chiral centers present, which means in total the number of optical isomers present would be 2 raised to the power of 2, which is equal to 4 optical isomers present for this compound. And this is how we identify chiral centers and obtain the number of optical isomers present for a particular compound if it contains any chiral centers.